Welcome back to Calculus 2. In this lecture, we're going to introduce two of the most useful tests for determining if an infinite series converges. The tests are called the ratio and root tests. All right, now I consider these to be the two most useful simply because whenever you're given an infinite series through this course, maybe elsewhere in the calculus sequence or beyond, chances are one of these two tests, either the ratio or root test, will give you a conclusive result on if it's convergent or divergent. Okay, let's go ahead and get into what these tests are. These two tests are kind of stated introducing a new type of convergence called absolute convergence. So we kind of have to kind of explain what that is before we get to the ratio and root tests and their statements. So let's think we have our old or first way to understand what it means for an infinite series to converge. So this goes back to our definition. The word mean here, what does it mean? We mean, what does it mean mathematically? And we did give a precise definition for what it meant for an infinite series to converge. The limit of the sequence of partial sums exists. Now we haven't used that in quite a while because we've been developing these shortcuts, these tests for convergence or divergence that tells us directly if an infinite series is convergent or divergent without having to look at the sequence of partial sums S sub n. All right, what we're going to do now is introduce another type of convergence. So when we say an infinite series converges, that means technically the sequence of partial sums has a limit. Now, when we introduce this new idea called absolute convergence, this means something else. And the word absolute here is referring to absolute value. So let's go ahead and give the statement of what absolute convergence is, kind of the mathematically precise definition. And we say an infinite series is called absolutely convergent if the infinite series where the term a sub n has been replaced with the absolute value of the term a sub n, if that's convergent. So basically what we do is we take our infinite series with the term a sub n, that could be positive or negative, and then we look at the infinite series where all the terms are now the absolute value of a sub n. And the absolute value of a quantity is never going to be negative. So that kind of gets rid of any alternating negative signs that might pop up with any infinite series terms. All right, so again, keep in mind here, absolute, or the word absolutely, is referring to absolute value. All right, let's take a look at some examples just to get a sense for how absolute convergence ties into our first notion of convergence, or our basic notion of convergence. So let's say we have an infinite series here where the term a sub n is alternating, and it's -1 to the n plus 1, that's your alternating term, divided by n squared. All right, now we already have covered the alternating series test. If you apply the alternating series test here, you'll find this infinite series is convergent. And just to be clear, the alternating series test tells us about our basic notion of convergence rather than what we're learning about now, absolute convergence. So by applying an old test, the alternating series test, we find this is convergent. All right, let's see what we can determine about this infinite series being absolutely convergent, which is what we're introducing. So if we take our term a sub n, absolute convergence wants us to look at the absolute value of the terms and the infinite series with those. So if we put our term here in absolute value, the alternating term, -1 to the n plus 1, that is only ever going to return the values +1 or -1, depending on if the exponent is even or odd. And when you take the absolute value of a negative, it just becomes positive. So to simplify this absolute value of a sub n, the absolute value of the alternating term is just going to be positive 1. And since our indices start with n equals 1 and go up towards infinity, n is only ever going to be positive anyway. Wouldn't matter here since we have n squared. Squaring a quantity is always going to be positive, but that could make a difference if the exponent, instead of being 2, were 3. All right, this is a long-winded way of just saying the absolute value of a sub n simplifies to just 1 over n squared. Now, if we look at the infinite series with the absolute value of a sub n, what we get here is a convergent p-series. The exponent of n in the denominator is 2, and you might recall for a p-series, if the power p is greater than 1, then your p-series is convergent. Now what this tells us is our series, because the terms in absolute value lead to a convergent series, this tells us that our infinite series is absolutely convergent, since the infinite series with the absolute value of terms is convergent. Okay, let's take a look at another example. The primary example that's usually brought up when absolute convergence is brought up in a Calc 2 course is the alternating harmonic series. All right, so let's take a look at what maybe the alternating series test tells us. We saw earlier that it says that the alternating harmonic series is convergent. All right, so we know something about this infinite series. It's convergent by our basic or first notion of convergence. Let's take a look at seeing what this determines for being absolutely convergent. All right, so if we take our term here, put it in absolute value, it's kind of the same as our first example above. We can take the absolute value of the alternating term, and that's just going to become positive 1. N, or the absolute value of n, is just going to simplify to n. Here, the indices don't have any negative values, so the absolute value of n is just n, and the absolute value of the term here, a sub n, just simplifies to 1 over n. Now, if we look at the infinite series where the term's given by the absolute value of a sub n, what we get is the harmonic series. And this is an important example. The harmonic series is a divergent infinite series. Now, what this tells us, since our infinite series with absolute value around the term a sub n is divergent, that means our infinite series is not absolutely convergent. But we do know from the alternating series test that our infinite series is convergent. So there's a difference between what convergence means and what absolute convergence means or tells us, which we'll be kind of elaborating on in a little bit. All right, now there's a term for what we have here in example 2. The alternating harmonic series is convergent, but we found here it's not absolutely convergent. Any infinite series that satisfies that, where it's convergent but not absolutely convergent, we call that conditionally convergent. So just keep track of all the terms here, what it means for an infinite series to be convergent, absolutely convergent, and now conditionally convergent. This is usually where students can sometimes get confused keeping track of all the terms. All right, now we use the last two examples to see that there is a kind of direct correspondence between infinite series being convergent and or absolutely convergent. Here is our first main result, which gives us some idea of the relationship between convergence and absolute convergence. Now, we're not going to prove this, but what the theorem states is if we have an infinite series that is absolutely convergent, then that same infinite series is also convergent. So what this theorem says is absolute convergence implies basic convergence, our first notion of convergence, the limit for the sequence of partial sums converging. All right, now this is a kind of a first place within the calc sequence of what you might be encountering as you continue your journey through higher level mathematics courses. And what's typically said is absolute convergence is a stronger type of convergence. And what we mean by that is there's more requirements on an infinite series to be absolutely convergent than an infinite series to be just convergent. We'll kind of, again, see this as we continue once we get through some examples after certainly stating the ratio and root tests. Those two tests tell us about absolute convergence. All right, now before we get to stating the ratio and root tests, this is a good point for us to introduce factorial, or the factorial of a positive integer. Right, and this is pretty simple to define. For a positive integer, we define the factorial of that to be the product of all positive integers less than or equal to that number, basically all the way down to 1. Now, you might have encountered this factorial if you've ever done any courses dealing with combinations or permutations. You first might have encountered n factorial as the number of ways to arrange or order n objects. So if you have, let's say, n people, and you want to arrange them all in a line, there's n factorial different ways to line up n people. And it's slightly more complicated to get this result here, what's called n choose k. Kind of referred to combinations and permutations. This expression, n factorial divided by n minus k factorial times k factorial, this tells you the number of ways that you can take k objects and select them from a set of n objects. That's something you'll get to when referring to permutations and combinations, maybe in a kind of a statistics course. All right, let's take a look at a few values just to get a sense of what n factorial is in terms of terms. So let's start with, let's say, 1 factorial, kind of the smallest positive integer. And simply 1 factorial, we just multiply 1 and that's it, and 1 factorial is 1. Now when we go up to 2 factorial, we start with the positive integer 2 and then multiply down, just ending with 1, since there's only one positive integer less than 2, which is 1. So 2 factorial we find to be 2. You can probably see the pattern here. 3 factorial, we define that to be 3 times 2 times 1, which is 6. And then the terms quickly grow from there. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720, and then they just start to grow very fast beyond that. Now, in order to apply this to what we're going to see in this course with the ratio and root test, some things we'll be getting to later when we start talking about power series, we have to define 0 factorial. And there's a few ways you can do this. The standard way is 0 factorial is defined to be 1. And that's just needed for some, I'll say, counting arguments with permutations and combinations to come out correctly. So as of right now, just accept 0 factorial to be 1. All right, now there is kind of some important properties here. If we take a look at those factorial values going from 2 factorial upwards, there is an iterative or recursive property to the factorial function that we're seeing here. So let's take a look at the factorials, 2 factorial up to 6 factorial, and notice something. If you take a look at 2 factorial, 2 times 1, you can write that as the integer 2 times 1 factorial. If we move on to 3 factorial, notice you can write 3 factorial as the integer 3 times 2 factorial. You can write 4 factorial as the integer 4 times 3 factorial, and then so on and so on. So what this basically says is for any factorial value, you can rewrite it as that integer, or in other words, n factorial, you can write that as the integer n times the previous factorial. And what comes before n? N minus 1. What would come after n would be n plus 1 if we're thinking of ordering of integers. All right, so we have this important property that we're going to be using pretty much anytime we encounter factorials. And the first version is that n factorial, we can rewrite that as the integer n times the previous factorial, n minus 1 factorial. That's the first version stated there. What's going to be useful for us when applying the ratio test, which we'll be getting to in a few moments, is to kind of relabel this. Instead of using, let's say, n factorial, maybe we would have n plus 1 factorial. Now, the second version is equivalent to the first property there. It's just a more useful version for what we're going to get to with the ratio test. So what it says is any factorial, you can write it as that integer times the previous factorial. If we start with n plus 1 factorial, if we think of n plus 1 as being the integer, what comes before n plus 1? N. So we can apply the first version and rewrite it as n plus 1 factorial equals n plus 1 times n factorial. It's specifically version 2 there that we're going to be using most times that we apply the ratio test. All right, and this is something that is very easy to program if you're familiar with basic kind of programming. It's probably just a few lines of code for like an if or for loop. And this is referred to for the factorial as the iterative or recursive property, kind of defining one factorial in terms of a previous factorial. Okay, let's go ahead and state what the ratio test is. The name, the ratio test, comes from we're looking at the ratio of terms. All right, if we start with an infinite series, for the ratio test, we have to make sure that we have an infinite series where the terms are non-zero. All right, if you take a look at that quantity L that we're defining as the limit as n goes to infinity of the ratio in absolute value, a sub n plus 1 divided by a sub n, since we're dividing there, we don't want to divide by a 0 value. So we just make the requirement that the terms a sub n are non-zero. All right, you can see here the quantity L is a ratio of terms. It's the ratio of a sub n plus 1 divided by a sub n. And just to kind of tie this into what we're mentioning about absolute convergence with absolute value, notice the ratio, that fraction, is inside of absolute value. Now, the nice thing about the ratio test is we get kind of a quantity that we can evaluate. We evaluate a certain limit here as n goes to infinity. And depending on that limit value, which we're denoting by L, we reach 3 conclusions. The first is if the limit value that you get is less than or equal to 0, or sorry, greater than or equal to 0, but strictly less than 1, then our infinite series converges absolutely. All right, the second possibility is if you get a limit value for L that's either greater than 1 or infinity, then the infinite series diverges. There is the possibility that the limit comes out to equal 1. If that occurs, the ratio test is inconclusive, and we would just apply another test. Okay, now just to be clear how this works, in infinite series, we're given the general term a sub n. How we apply the ratio test is we take a look at the term a sub n plus 1, replace all n's everywhere in your term with n plus 1, and then we divide a sub n plus 1 by a sub n and put that all in absolute value. The absolute value is only going to matter if you see alternating terms or if any of the terms could be negative. And then once you have that absolute value of the ratio, we just evaluate a limit. Now this might right now all sound like a lot, but it's very straightforward in the sense of take your term, replace n with n plus 1, form the ratio, put it in absolute value, and then take a limit. And the ratio test here has some very nice conclusive values or conclusive results depending on the value of the limit that you get. It tells you directly if your infinite series is absolutely convergent, and it also tells you if your infinite series is divergent. All right, the root test, which is the second test that comes along with the ratio test, is very similar, but the name root test has us look at the nth root of the terms a sub n. So if we have an infinite series here where the term is a sub n, we don't have to make any requirement for the root test that the terms are non-zero. And what we look at for this quantity L is no longer a ratio, but we look at the nth root of the absolute value of the term a sub n. Now, just to keep in mind the nth root, you can see in red there, you can rewrite an nth root as a 1 over n power. Now, the reason why the absolute value is needed here, just think certain radicals or roots, if they are even, can kind of lead to some problems if you're dealing with negative values inside. Like just think the square root of -1 is undefined as a real number. So if we put absolute value around our term a sub n, then we get rid of any possibility of there being a negative inside that possibly even root or radical. These are just more technical things that happen for a few examples, but not all of them. All right, so it's the same, pretty much same three conclusions from the ratio test. For this quantity L, we take a limit now as n goes to infinity of the nth root of the absolute value of a sub n. So a slightly different limit expression that we're evaluating, an nth root versus a ratio, but it's the same three conclusions. If that limit L is greater than or equal to 0 but less than 1, then our infinite series is absolutely convergent. If the limit L is greater than 1 or equal to infinity, the infinite series diverges. And if the limit value equals 1, the root test is inconclusive. And we will just apply another test. All right, at this point, we're going to jump to some examples. Pause the video maybe to copy these down into your notes, just to refer to as we go through these next set of examples. All right, so let's go through part A together. Once we go through part A, I'll have you pause the video to make an attempt at parts B, C, D, and E. And the question is just simply going to ask, for each infinite series, determine if it converges or diverges. Now, just to tie in the ratio and root test, they actually tell us more than basic convergence. If the limit is greater than or equal to 0 but less than 1, L, then the ratio and root test actually tell us that our infinite series is absolutely convergent. How does that relate to regular convergence? Recall our first theorem, first result in this lecture. We said absolute convergence implies convergence. So if we can apply the ratio or root test and we get the limit value being greater than or equal to 0 but less than 1, then it converges absolutely, which implies our infinite series convergence. All right, let's go through part A. Before we do that, there's some tips I want to kind of have you keep in mind as you go through these different examples when you get to parts B and beyond. And the first is typically anytime there is a factorial, that is almost always an infinite series where you would want to apply the ratio test. And that's due to our recursive or iterative property of factorial. n+1 factorial can be rewritten as the integer n+1 times n factorial. That's that second tip there. The ratio test when there's factorials and that second property there, that second tip, usually go hand in hand. All right, some of the terms here involve a number raised to an nth power. This is the third tip. And if you were to replace n with n+1 with the ratio test, you might get a number raised to now the n+1 power. That's no problem. We can rewrite that. Reverse basic properties of exponents. A number a to the n+1 power, you can rewrite that as a to the n times a to the 1, or anything to the first power is just that number, in this case a. So when you're applying these ratio and root tests, keep in mind these tips and tricks, particularly dealing with factorials and a number raised to an nth power. All right, with these tips in mind, let's get to part A. Since we have our term as 1 over n factorial, that's kind of tempting us to want to apply the ratio test. So let's go ahead and do that. We take a look at our term a sub n, which is 1 over n factorial. We're going to replace anywhere there's an n in that general term with n+1. Here it's only in the denominator, so n factorial increments or goes up to n+1 factorial when we make that replacement. Now, to make the algebra in simplifying the ratio of a sub n+1 divided by a sub n as simple as possible, let's apply our iterative factorial property, and we'll rewrite that denominator as n+1 times n factorial. That's a common step when applying the ratio test with factorials. All right, we're going to take a look at the ratio of a sub n+1 divided by a sub n in absolute value. Notice here both a sub n and a sub n+1 are both fractions. So when we divide, specifically dividing by a sub n is a fraction, we can multiply by its reciprocal. So instead of dividing by 1 over n factorial, let's multiply by the reciprocal, n factorial over 1. All right, now that we've applied our iterative property of factorials, notice in that ratio, the n factorial factors cancel out. The quantities inside are only positive, so the absolute value bars don't really matter. Absolute value of a positive number is just that number. And this whole mess of an expression just simplifies to 1 over n+1. All right, now what we look at is the limit of that ratio. And if you take a limit as n goes to infinity, 1 over n+1 approaches 0 since your denominator is getting bigger. All right, and that falls into the first conclusion of the ratio test. The limit value is 0. And since that's in that first part, the limit being greater than or equal to 0, but less than 1, this tells us our infinite series is absolutely convergent, which implies the series in question is also convergent, which is what was asked. All right, hopefully this example gives you a sense of how this all fits together. At this point, pause the video and give yourself an attempt at parts B, C, D, and E. We'll check in a few minutes. All right, welcome back. Let's go through part B. This one, while there is no factorial present in the general term a sub n, even though there's no factorials, we're still going to apply the ratio test. More times than not, it is the ratio test that's easier to apply than the root test. All right, so we're going to take a look at applying the ratio test. We take our term a sub n squared divided by 2 to the n, and we increment it, replace all n's with n plus 1, and notice in that denominator you get 2 to the n plus 1, which we're going to rewrite as 2 to the n times 2. That's our third tip when we started these examples, breaking up an n plus 1 power as an nth power times the number. All right, notice both a sub n and a sub n plus 1 are fractions, and this is going to happen for a lot of examples. So when we divide here in the ratio by a sub n, we can multiply by its reciprocal. That's a good habit to get into. When you divide by a sub n, multiply by its reciprocal. So we multiply here by 2 to the n divided by n squared. All right, and notice if you simplify that, the 2 to the n factors cancel out, and you get for your simplified ratio, again, the absolute values here doesn't matter since the terms inside are only positive, you get for your simplified ratio n plus 1 squared divided by 2n squared. At this point, we can now take a limit for that as n goes to infinity. The technical way to see this would be maybe applying L'Hopital's rule. That's kind of like a sledgehammer when dealing with limits that have indeterminate forms. Hopefully you can see maybe a little bit more quickly here. If you were to multiply out that numerator, n plus 1 squared, the highest power you would have there is n squared. There's also an n squared in your denominator, and since the degrees are equal, n squared, in both numerator and denominator, the limit as n goes to infinity should be the ratio of the leading coefficients. And we just find here the ratio of those coefficients of n squared would be 1 over 2, so we get our limit here as a half. All right, and a half is less than 1, so this tells us by the ratio test that our infinite series is absolutely convergent, and that thereby tells us our infinite series is convergent. All right, let's move on to part C. Part C, we are again going to apply the ratio test. It's very similar to the last example. Our term a sub n is 2 to the n divided by n cubed, and it's the same kind of example again, same trick. You can replace in that numerator 2 to the n plus 1, rewrite that as 2 to the n times 2. Same thing here, when we divide, multiply by the reciprocal, and you should get a simplified ratio here of 2n cubed divided by n plus 1 cubed. Like the last example, for this limit as n goes to infinity, you can apply L'Hopital's rule, or notice the highest power of n in the numerator and denominator are both n cubed, so the ratio here of the leading coefficients should be 2 over 1, which is the limit. 2 over 1 is just 2 here. All right, and since this limit is greater than 1, this falls into the second part of the ratio test, which says that your infinite series would then be divergent. All right, let's move on to part D. And for this one would lead to a rather complicated expression if we were to try to apply the ratio test, since we have in the denominator n raised to the nth power. If there are only nth powers, that's a usual hint that you might want to apply the root test. The root test would have you take an nth root of that expression. Nth roots and nth powers will cancel. All right, so if we take our term a sub n as -1 to the n plus 1, divided by n to the nth power. First, we take the absolute value. That knocks out the alternating term. That just simplifies to 1 over n to the n. And when we now take the nth root of the absolute value of a sub n, you can basically just take the nth root of the denominator, and the nth root and the nth power cancel out, leaving you with just n in your denominator. Now, if we take a look at the limit of that expression as n goes to infinity, 1 over n approaches 0. And again, that falls into our first result for the root test. When the limit value L is greater than or equal to 0, your infinite series is absolutely convergent, which tells you that your series is convergent. All right, let's finish with part E here. This one is another example where we apply the ratio test. Factorial gives us that hint. And it's very similar here. The only kind of new part is notice a sub n in the denominator already contains n plus 1 factorial. Now, if you replace and increment n in that expression with n plus 1, you get n plus 1 plus 1, which just simplifies as n plus 2. So here we have an n plus 2 factorial in that denominator. Now, to simplify before moving on, we can apply our iterative property of factorials to rewrite n plus 2 factorial as the integer n plus 2 times the previous factorial. What comes before n plus 2 is just n plus 1. So that's where the n plus 1 factorial comes in. All right, same tricks as before. When we take a look at the ratio of a sub n plus 1 divided by a sub n, we can multiply by the reciprocal, and we find here that our ratio just simplifies to n plus 1 divided by n times n plus 2. If we take a look at a limit of that as n goes to infinity, you'll find that limit approaches 0 since there's kind of higher powers of n in the denominator rather than in the numerator. You could also apply L'Hopital's rule. All right, you get here that your limit is 0. That tells you that your infinite series is absolutely convergent, which would imply that your series is convergent. All right, hopefully you get a sense for how the ratio and root tests are applied. What I want to close this lecture with is just a very brief explanation of the role of absolute convergence and conditional convergence. So let's take a look at two examples here. We have these from the intro. The first one is absolutely convergent. And then we have the alternating harmonic series, which is conditionally convergent. Now, what's special about the alternating harmonic series is we did state earlier without proof that the sum is natural log of 2. So in that order, 1 minus a half plus a third minus a quarter plus a fifth, that sums to natural log of 2. Now, there's a result in mathematics called the Riemann rearrangement theorem, which basically says for any conditionally convergent series, there is a rearrangement of terms that converges to any real number. What that means for our conditionally convergent series, the alternating harmonic series, in the basic version, 1 minus a half plus a third, so on, the terms sum to natural log of 2. If you rearrange it, you get a different sum. Highly counterintuitive, which is what makes conditionally convergent series a bit weird, whereas absolutely convergent series are nice. If a series converges absolutely, the rearrangement gives the same sum.